Hello and welcome to another video in general design engineering. In this video, I'll be taking you through on a very important tool set for design engineer, which is DFMEA, Design Failure Mode Effect Analysis. So what exactly is it and how exactly does it help design engineers? We will see in this video. We'll be taking an example of a shock absorber and going through the process as well, how to create a DFMEA. So first, let us understand that all the mechanical systems which we design, which have been designed through history, have the tendency and will fail. Mechanical systems can and will fail, and risk is always associated with the design. Whatever you design, there is a chance that it will fail, and risk must be accounted and calculated. It is very important for businesses, for product development organizations to account for the risk and calculate the risk which they are taking when they are designing systems and when they are implementing it. And this risk increases with the stage of the product. So when the product is in the design stage, the risk is generally low, because if you find any failure mode, you can correct the design, and then that risk becomes lesser. But as we go towards the next stage of the product development, that is when the design has been implemented and taken through the production stage, then the risk associated with that design or that mechanical system increases greatly, and it increases even more when it is in the hands of the customer, that is after sales. Hence, risk is something which has to be accounted for, and risk is in the form of probability of failure. So how do we account for the risk and how do we document it? That is what DFMEA does. So when we say failure, failure can be a structural failure. For example, if in a chassis the bracket breaks, or if in a suspension system the control arm breaks, that's a very severe failure. That's a structural failure. But failure can also be in other forms. It can be degradation of the function. For example, if a vehicle is having a top speed and an acceleration, and through time the top speed and acceleration actually reduces for the vehicle, it is a form of failure, but it is not as severe as structural failure. And also failure can be in the form of corrosion or environmental degradation. So there are different forms of failure, different levels of failure. So how do you assess the risk? There are three factors which help us to assess the risk. One is, how severe is it? What's the severity of the failure? So does it affect the safety? For example, in a car, if a control arm breaks, it directly affects the safety of the passengers. So that's a very, very severe failure. Or is it regulatory compliant? So regulatory compliance is the compliance to the rules and regulations of the nation or the land where the product is being sold or where it is developed. So if it is not compliant with the rules and regulations, then it is a top level severity. The next level would be loss in function. Is a failure mode causing loss in function? Basically, if let's say there's a car and the engine seizes. Now the seizing of the engine it might not affect the safety, although actually it can affect the safety if it happens during the running. But if it happens when the vehicle is stationary, it is loss of function. The vehicle is not able to operate. Or let's say any type of failure which impedes the operation of the vehicle is loss of function. The next level will be degradation of function. The function is taking place, but it is at a much lower level as compared to what it's supposed to be. So that is severity. Next is occurrence. How often does it occur? Does it occur always? Does it occur occasionally, seldom, or hardly it occurs? The level of risk, of course, is highest when we consider the occurrence to be always, and it is lowest when the occurrence is rare. The next factor is detection. How easy is it to detect that failure mode in design? Let's say, for example, if you're having a design of a bracket, and by looking at the bracket itself, you can make out that the material is very thin, and it is just by looking at it, you can predict that it will fail. It will not take the load. So that's the easiest part of detection, that you can make out by visible inspection of the design. It is obvious. But what if you require some amount of design review and some amount of analysis? That's the next level. And if you require physical testing, If you have to make a prototype to actually check whether a failure mode is occurring or not, then that level is a higher level of detection. And if you require a thorough analysis, thorough investigation, thorough testing for the product to actually identify failures, then that is even higher. And the highest would be when the failure mode is undetectable. You are not able to detect the failure mode even through testing, even through detailed analysis, even through design reviews. You're not able to detect it. That's the highest level of risk. So a failure mode which compromises safety or compromises regulatory compliance is occurring always and is very difficult to detect is the highest risk. Here is a very simplified workflow on how to prepare a basic preliminary DFMEA for any product or system. The first step and the most important step is actually to understand the system thoroughly. We need to understand the system thoroughly to actually make a good DFMEA. Without understanding the system, without understanding the boundaries, the functions, the parameters which govern the design of the system, we will not be able to create a good DFMEA. So the first step is always to understand the system, the boundaries, the scope within which we are operating, the boundaries with respect to how it interacts with external elements, how it interacts with external systems, the functions of the system, what it is supposed to perform, what are the requirements, and the parameters which govern the design and which govern the output of the system. Next, investigate and list the possible failure modes. We basically investigate and list the possible failure modes which can occur or which have occurred for the product or the system, depending on prior knowledge or depending on new tests which we are performing on the system, or basically prediction of failure modes which can occur. So you investigate and list the failure modes and their effects. So a failure mode is the mechanism of failure and the effect is what happens because of that failure at the end product or the end result of the product. Next is we investigate the causes of the failures. What are the probable causes for the failures? What are the root causes? What is causing the failure mode, which in turn is causing the failure effect? So cause, mode and effect. Next, after finding out the failure causes, we list them down corresponding to the failure modes, and then we assess the risk posed by the failure modes. So each and every failure mode will have a certain risk associated with it, as we had seen: severity, occurrence and detection. We assess the risk corresponding to that failure mode, and then we implement the action plans for correction of the design, for improvement of the design through testing or analysis. Through analysis or testing, we find out these failure modes and then we improve the design and then release the improved design. So that's a general workflow for a DFMEA for a design engineer. So if you want to learn more, I have created a DFMEA reference ebook which has all of these slides in this video, as well as more information on DFMEA, how it is made, what are the various steps in DFMEA in much more detail. You can download that ebook, which is there in the description below as a link. Now let's go through a very basic DFMEA of a shock absorber. A shock absorber is an automotive component. It is used in vehicles, cars, bikes for the purpose of damping the vibrations which are coming from the road and providing a good ride and handling characteristic for the vehicle. So the scope here, of course, this is a very simple DFMEA. We're not going to go too much into the details. We are developing a preliminary DFMEA for a standalone shock absorber for a vehicle. The first step is to understand the system. In order to understand the system, you need to understand what are the parts of the system. Hence, the first step is to understand the structure, which is called as the structure tree. So the shock absorber consists of the damper assembly, the spring, the top mount assembly and the bottom mount assembly. So if you look at this image, so this is the top mount assembly, which is having a bush which is going to connect to the chassis. This is the bottom mount assembly, which is having again a bush and a hole which connects to the control arm of the suspension system. Then we are having the damper, which is this cylinder inside, and this rod that is part of the damper assembly. And then we are having a spring, which is a red color, which is connected to the top and bottom mount. And basically this is the assembly. This is a top level assembly. Damper assembly will have a cylinder which is shown over here, which is have piston rod assembly, which is again over here, and that piston rod assembly will have a valve attached to it which is doing all of the function of the damper. So the valve is performing the function of restricting the flow and hence creating the damping effect of the damper assembly. The spring is clear, it is the red color part. The top mount assembly has a mount and a spring seat, which is basically where the spring is sitting, and then the bush housing. Bush housing is this, and then the bush is there, which is inside, which is press fitted inside it. Similarly for the bottom mounting as well. So this is a basic structure of a shock absorber. Next, let's have a quick look at the boundary diagram. So the boundary diagram is basically showing the interactions of the shock absorber assembly with the external components or external system which is having interface with. So the shock absorber assembly is part of a larger system which is the vehicle, and the shock absorber assembly is assembled onto the chassis and onto the control arm, suspension control arm, as shown over here in this image. So the shock absorber assembly goes over here, it is connected to the control arm at the bottom and the chassis at the top. So in creating the boundary diagram, setting the interfaces, so this is the box which shows the boundary, and the suspension control arm is having a direct connection with the bottom mounting of the shock absorber. So it has having a physical connection where the mechanical energy transfer takes place. That is, the energy coming in from the wheel will go through the control arm and go through the shock absorber. That is a energy transfer taking place. Similarly, from the chassis as well, similar physical connection is there as shown over here. Top mounting, physical connection, and energy transfer, load transfer. The top mounting has connection to both the spring and the damper. The damper is this shown over here. So this is the internal working of the damper, which is having a valve system connected to it, and it is having a rebound and compression valving system, and it has rod guides and seals inside it. So basically this is the internal construction of the damper, which is this over here. And that damper is connected to the bottom mounting, it's connected to the spring mounting, it's connected to top mounting. So it's connected to all of these systems. The spring is connected to the bottom mounting, and basically there is a heat transfer taking place between the damper and the environment. So the heat, when the damper is working, it is moving up and down, heat will be generated, and that heat will be given out to the environment, which is shown over here in this hash line. This is the energy transfer, heat transfer taking place outside the boundary. So this is a very basic boundary diagram for a shock absorber for understanding purposes. The next step is to perform the function analysis, in which we are investigating and listing down the primary and secondary functions of the system, and also the non-functional requirements of the system, which are not related to any function, but they are required as a part of any mechanical design consideration. So primary function, the first is damping oscillations. That's the most primary function of a shock absorber. The main purpose of a shock absorber is to damp the oscillations which are coming in, to reduce the amplitude of the oscillations which are coming in, and also to maintain the tire to rod contact. This is also a very important function which is associated with the shock absorber. So the damping of the oscillation should not be as such that the tire to rod contact is lost. It should also maintain the tire to rod contact when it is damping the oscillation. So these two are the most primary function of the shock absorber. Secondary function, controlling the vehicle body motion. This is an indirect function of a shock absorber which is related also to the suspension geometry and the overall vehicle architecture. So controlling the vehicle body motion is a secondary function. Improving the ride comfort is of course a part of the primary function, or we can say a secondary part of the primary function, which is damping oscillations, improving the ride comfort. Reducing wear on suspension components is also a secondary function, and dissipating kinetic energy as heat is also a secondary function. As we have seen earlier, the damper, when it works, it gives out heat, and that heat has to be dissipated. The kinetic energy of oscillation is converted to heat. So that's the secondary function. Now about the non-functional requirements, regulations of course is very important. Regulations are the rules and regulations of the country in which the vehicle or the vehicle is being sold. So the regulations have to be followed. There are regulations with respect to shock absorbers which have to be followed, or with respect to suspensions. Durability and reliability is a general requirement. The shock absorbers need to be durable, they need to be reliable, they need to perform their function at the highest level consistently. Serviceability is also very important because shock absorbers require to be serviced frequently. So serviceability is important. Another important non-functional requirement is noise, vibration and harshness. Actually, this can become a secondary function if the NVH is very critical. But we are listing over here in non-functional requirements because it does not directly affect the function, but it can affect the function in a secondary or tertiary manner. So NVH is basically the noise and vibration which is created by the damper or created as a result of the damper or the shock absorber, which has to be reduced for a vehicle. NVH levels have to be reduced for a vehicle. And then there are non-functional requirements regarding the assembly. So again, related to serviceability, assembly of the shock absorber on the assembly line is a non-functional requirement. Now we are going to look at the parameter diagram for the shock absorber, which is part of understanding the systems. So in order to understand the system, we need to understand what are the inputs to the system, what is the intended output, what is the unintended output, and what are the factors which affect the performance. And of course, along with that, we need to also list what are the important functions which it needs to perform. So first, what is the input to the shock absorber? Technically or functionally, the input to the shock absorber is the vertical displacement or velocity which is coming in from the control arm. So the control arm is connected to the wheel and the wheel is contacting the road. So as the road undulations are transferred to the wheel, that is transferred to the control arm and hence transferred to the shock absorber in terms of vertical displacement and velocity. And of course, there is a force which is associated, which is the impulse force which is acting on the shock absorber. So the force, the displacement and velocity are the input. Actually, the force and the velocity is the input and the displacement happens as a result. So these are the inputs. Now, the intended output for the shock absorber in terms of its functional performance or in terms of its purpose is that it should generate required damping force based on the velocity. So based on the velocity, it should generate the required damping force and also dissipate the energy and stabilize the vehicle. That is the intended output what the shock absorber should perform. The unintended outputs are excessive heat. The shock absorber is generating excessive heat. The shock absorber is generating excessive acoustic noise. It is very noisy in operation. There is some form of fluid leakage which is happening in the shock absorber, or the shock absorber is not performing its function, it is transmitting the vibrations. So these are unintended outputs. Now, as we have seen earlier, what are the functions, what are the functional requirements? These are the primary and secondary functions: damping spring oscillations, maintaining tire to road contact, controlling vehicle body motion, improving the ride comfort and dissipating the kinetic energy as heat. These are the main functions of the shock absorber. Now, in terms of design, in terms of the technical design of the shock absorber, what are the control factors? What are the factors which we control to change the output of the shock absorber by design? These are the factors. Spring specifications, of course, that is a major specification. The spring specification, the height, the coil dia, the number of turns. The spring specification, if we change that, we change the performance of the shock absorber as a whole. The damper stroke, the length of the damper, that also has a direct implication on the performance. The mounting arrangement design, the top mounting and bottom mounting, how they are mounted. The orifice geometry, so this goes into the details of the valve design which is there inside the damper. The orifice geometry, the shim stack configuration, again it is a part of the valve design. The fluid viscosity, the fluid which is used inside the damper, the viscosity of that fluid directly affects the performance. If there is any pre-charge gas which is there, which maintains the pressure inside the shock absorber or inside the damper, then what is the pre-charge of that gas, the level of pre-charge, level of pressure because of that gas pre-charge, that is another control factor. The piston and rod diameters, the design specification of the piston and rod directly affects. Seal material and preload, the seal sealing of the shock absorber will also have a direct implication. The bush design and material. So these bushes, what are the materials, what is the type of rubber which is used, or what is the type of elastomer which is used, what is the configuration of the bush. So those aspects. So these are the control factors, which is nothing but the design parameters which you control as a design engineer for the performance of the shock absorber. Then there are non-functional requirements which we had seen earlier: compliance, regulatory compliance, durability, reliability, serviceability, usability, safety, aesthetics, cost and weight. So all of these are non-functional requirements, which are not directly related to the main function, but are also very important. Next, we have noise factors. So these 5 categories are called as noise factors. These noise factors are the sources of variation in the output or performance of the system which are not in control of the design engineer. These are called as the noise factors. Noise factors are external to the system, or we can say that not in control of the design engineer. These are factors which are in control of the design engineer, the control factors. But these are the factors which are not in control of the design engineer. One of them is piece-to-piece variation. So the dimensional tolerances, of course, the tolerances which the design engineer sets is one thing, but what the tolerances can be achieved is another thing. So dimensional tolerances which are actually achieved on the part, on the shock absorbers, the fluid fill volume, because that happens on the assembly line and is not in control of the design engineer, it's control of the manufacturing. The surface finish which is being maintained in manufacturing, the spring rate variation which is caused due to the manufacturing. So the design engineer specifies one spring rate, and in the manufacturing there is of course a range. We cannot manufacture at one single spring rate, there is a variation. So that variation is not in control of the design. Then change over time. So as time passes, as the shock absorber is used for years, the fluid degradation will happen, seal wear will happen, there will be valve fatigue and corrosion which will take place, that will degrade the performance. The third noise factor is usage. The way the vehicle is being used, the way the shock absorber is being used is not in control of the design engine. The vehicle payload, what the vehicle is loaded to, of course the shock absorber is designed for a specific gross vehicle weight or laden weight. But what if the vehicle is loaded more than that? The vehicle payload, the driving style also has a direct influence. The way the driver is driving the vehicle, the driving style, the duty cycle, the number of hours the shock absorber is being used, extreme use cases or misuse of the shock absorber, that is also not in control. Environment is of course temperature extreme. So the shock absorber is generally designed with a certain temperature range in mind. For example, minus 30 degrees to 80 degrees Celsius. What if the vehicle is being used in extreme temperatures, minus 30 degrees Celsius? What happens? Chemical exposure. What is the result of chemical exposure to the vehicle? For example, the bushes, the elastomers, if they are prone to reaction with chemicals, then they will wear out and that will degrade the performance of the shock absorber. And the effect of dust accumulation, how does it affect? For example, if too much dust is accumulated in the damper, then that will impede the function of the damper. System interactions are interactions which are external to the boundary, which we have seen, the boundary of the shock absorber, external to the boundary. What are the interactions and how changes in those interactions is affecting the performance? For example, tire stiffness. Tire stiffness will have a direct implication on the performance of the suspension as a whole. So tire stiffness and the spring stiffness are basically in series, hence they perform overall for the vehicle dynamics of the vehicle. Suspension bushings also should work in unison with the damper bushings or shock absorber bushings, hence any change in that will cause change in the overall performance. Chassis stiffness also has a bearing, because the spring stiffness and the chassis stiffness has a relation in the overall dynamics of the vehicle. The control arm geometry has also an implication, although a minor one. Sprung mass versus unsprung mass, this has a very direct implication on the shock absorber design. The next step is preparing a preliminary DFMEA. So here is a preliminary DFMEA. Of course, this is not a final DFMEA, not a complete DFMEA. It's just for demonstration purposes for the shock absorber component. So this is the format. the first column is item slash function. Item indicates the item or the subassembly which we are dealing with, or the component which we are dealing with within the shock absorber, and the function of that component or subassembly. So the function which we are dealing with, function is of course taken based on the primary and secondary functions which we had found out during the creation of the parameter diagram. So that function comes over here, and item indicates that subassembly for which the failure mode occurs. So in the first line it is piston rod which is part of the damper assembly, and the function with which we are concerned is transmitting forces from suspension to the valve assembly. This is of course a sub function of the damper assembly. The potential failure mode which will occur is rod bending. So if the rod is bending or buckling, that is a potential failure mode. What is the effect? The effect of the bending of the rod will cause loss of damping and potential interference with the housing and vehicle instability. So if let's say the damper is operating and the rod bends or buckles, we have a loss of damping, we have a potential interference with the housing or interference with the interfacing parts. The potential cause of that failure can be side loading, which is creating a buckling load or a bending load on the rod because of extreme suspension travel, or the rod diameter is insufficient in terms of the static design or static loading design for the damper. Insufficient rod diameter, that can be a potential cause. So giving a occurrence rating depending on whatever the knowledge we have regarding the system. Of course these ratings might change as we learn more and more about the system. If we are having a low occurrence, that is it hardly occurs, that is occurrence is 2. And then the next column is current design controls. What are the controls which we have in design, in the whole design process, which basically avoids this failure? One of the controls which we have in design is FEA stress analysis. Basically you perform the stress analysis on the rod and check whether the side load is causing a failure or not. So that is one design control. What is prevention control? Prevention control is basically any design control which is there in place before actual physical parts are made, before prototypes are made. That is during the design phase itself, whether it is by just visually checking the design or by design review or by stress analysis calculations. All of these are design prevention controls. What are design detection controls? Design detection controls are actual physical tests which you are performing on the parts and then finding out the failures. So the FEA stress analysis is a design prevention control, whereas the side load testing, which is physical testing during validation, is design detection control. So there is a difference over here. And the detection rating is given based on how much we know or how much can we detect about the failure. So this is for the first line. Similarly, you can see for the line 2, line 3, line 4, there can be many lines like this, and you can have a very exhaustive DFMEA for a simple, not actually a simple, actually very complex shock absorber assembly. But this is just for understanding how the DFMEA is being created step by step. So if we just have a look at the second line, again we are dealing with the piston rod. Here the function is maintaining smooth surface for sealing, that is internal function of the rod. The rod should have a smooth surface for sealing. Potential failure mode is that the surface is being damaged, it is having scoring or pitting. The surface of the surface finish of the rod is not up to the mark. So that will cause accelerated seal wear because of the scoring and pitting on the rod surface. Fluid leakage will be as a result, and reduced service life. The potential causes can be that some debris has come into the contact with the rod, and the debris has caused scoring or pitting on the rod surface. Or it can be that there is insufficient chrome plating thickness. So the plating, the chrome plating on the rod, which makes sure that the surface finish is optimal, is not sufficient. That can be also a potential cause of failure. And certain design controls which are there are nothing but the material specification. So the material specification for hard chrome plating of the rod, this is a design control prevention, which is you are mentioning that in the design that the supplier has to maintain the material specifications as per the hard chrome plating. The hardness of the surface and the surface finish should be within that specification. That is what you are mentioning in the design. And what about the design detection controls? That is nothing but you are actually testing the shock absorber in the rig, on the suspension rig, and seeing if it is causing surface scoring or pitting because of debris. So that is actual you are checking on the suspension test rig. So that is detection control, actual physical testing. So basically you can see that the same is being repeated across different items and different functions. So in the third line we have the main oil seal, and the function of that oil seal is to retain the hydraulic fluid and nitrogen gas. And then the potential failure mode is that the fluid leakage. So the fluid leakage which we had seen in the unintended output is related over here in this failure mode. So if we get a fluid leakage in the shock absorber on the vehicle, we can relate it to the oil seal through the DFMEA. We will know that the leakage might have occurred due to a failed oil seal. So the potential effect of failure is that the loss of damping performance, environmental contamination, customer dissatisfaction. Potential causes can be that the thermal degradation of the elastomer has happened. The seal elastomer, the oil seal elastomer, which is used for making the oil seal, if that has undergone thermal degradation, then the seal would have failed. Or if there is very high internal pressure spikes, which is causing the failure of the seal. So the severity is 7. Of course, it's not the highest. It's 7. Fluid leakage does not directly result in issues of safety, but it results in reduced performance or degraded performance. Occurrence rating is generally low. It does not happen often. Detection rating is 5. It can be slightly, it's not that easy to detect, but it can be detected through testing. So the design prevention controls over here is sealed material selection. That is, the material selection aspect of the design is a design prevention control, because that is under the control of the design engineer. Then design detection control is high temperature endurance testing, in which we are actually physically testing the shock absorber and checking whether it is having any fluid leakage or not, or any loss of damping performance, which is related to the oil seal failure. So similarly, you can see the other items functions, the related failure modes, the potential effects, the severity ratings, the potential causes, the occurrence rating, the current design controls, prevention and detection, and the detection rating. This PDF, this slides will be available for download in the description below. You can check out the link. And also there is a lot more information apart from that in that reference book, which you can download and check it out. So I hope this video has been useful to you. This is just giving you an overview of the DFMEA. The main purpose of this video was to give an overview of the DFMEA, what exactly is DFMEA and how is it performed with an example. You can use this as a kind of a stage for diving deep into DFMEA, learning more about DFMEA.